everyone, my name is Erin Huang and I will be your lab instructor. Welcome to our SE350 RTOS lab. Our lab is project-based. In this first tutorial, Lab 0, I'm going to introduce you what this project is about and the development tools. First, I'm going to introduce you some general information about the lab. Our lab is in E22363. When we're back in person, we'll be inside this lab. Well, now we're doing online learning, so this lab is remotely accessible. In this lab, we have 27 Windows machines. Each one of these Windows machines is connected to this Keil board, this big blue square one. That's the Keil board. The board is a microcontroller, so this middle part, this is the main chip, NXP LPC1768 microcontroller. And if you look at the connection, the green cable supplies power from the host computer to the board. So we call this Windows machine the host computer because we do the development from this particular machine. And then there's this USB cable that connects to the end of this green board, which is an adapter that allows us to access the serial ports on this microcontroller through the USB from the host computer. And then you can see there's another USB cable that connects to this little board here. See the golden edge here? There's this size of a daughter board underneath this motherboard. This is the mechanism that allows us to download the code from the host computer through USB to the microcontroller. So the project is to basically write a real-time operating system kernel for this board, or more specifically, to manage this microcontroller. We break down the project into 3 pieces. As you recall, a microcontroller has memory, has a processor, and has I/O. So the first part, we're going to be focusing on the memory and the processor management. And the second part, we're going to focus on the inter-process communication by message passing and some timing service. And the last part, we're going to provide console I/O service to the end user. And then last is the stress testing part. You probably have seen this administration-related information in the lecture notes already, so I just want to remind you, we have 3 grace days for the term for you to delay your submission. However, there's no submission accepted after 3 days. And the other thing is, for any late submission, after you use up all your grace days, there's a 15% per day late submission penalty. And finally, our project needs to function on the real board, not just the simulator. If it only works under the simulator, but not on the real hardware, you get 15% of penalty as well. So let me talk about the lab sessions. We have 5 weeks of scheduled lab sessions in total. 2 of them are help sessions. Help sessions attendance is not mandatory. 3 of them are lab demo sessions. So the demo lab sessions are mandatory. We use these demo sessions to evaluate your lab deliverable. If the class finds extra drop-in help sessions are needed, then please let the class representative contact us. I'm going to talk about how we're going to operate these help sessions. Well, while we're online, from 8:30 to 10, these help sessions are drop-in sessions. I'm going to post a link to tell you where you can meet us online. And then for the second half of the lab session from 10 to 11:30 requires booking. And here's the link to do the booking. So each time slot is 15 minutes long. And usually one group will book 1 slot. But it's okay if individual students want to book a slot as well. Once we're returning to the campus in person, then from 8:30 to 11:30, the entire lab session is drop-in, so no booking is needed. Okay, so about the demo lab session, the demo lab session is from 8:30 to 11:30, and we requires booking. Basically, each group will book a particular time slot to demonstrate their project to us. Well, while we're in person, the P1 and the P2 demo slots are 30 minutes. However, for online offering, we add extra time for people to accommodate people for possible technical difficulty or network issues. So P1, P2 will be 45 minutes long. P3, I hope by that time will be back in person, and that will be 45 minutes. And if it is still online, that will be an hour. If you have questions, please ask us on Piazza. Please don't wait till the last minute to ask questions. Our target response time is 1 business day. We also run lab office hours during the weeks that we do not have scheduled lab sessions, and they are on Tuesday, Wednesday, Thursdays from 10:30 to 11:30. For now, it requires booking. When we're back in person, I will let you know whether we still need booking or not. We also accept individual appointment. Please email us. And be sure to put the subject line with this particular subject line, like SE350 LAB, your group ID. Your group ID is very important. Again, if the class find they need extra drop-in help sessions, please let the class representative contact us. I've uploaded the lab calendar for you on Learn. So it is color-coded. Anything highlighted in yellow, it is lab office hours. And for the light blue highlighted weeks, those are the help session lab weeks. And for the pink color ones, those are the demo weeks. So those are the demo weeks. And for the tutorial, lab tutorial, they are happening on Wednesdays, and I put a tentative schedule here. If it is online, then I can either do it as a pre-recorded video, so that basically means by this time the video will be there, or I can do like a live broadcasting. If it is a live broadcasting, it will basically happening at the time shown here. When we are online, the lab facilities are accessible through remote desktop session. First, you need to be on Campus VPN. Then you go to this website, englab.uwaterloo.ca. Select ECE, ECE RTOS. There are 27 computers in that lab, and I find it is useful to enable the multiple monitor support. It's just makes a lot difference, big difference when you do programming development. Lastly, please remember to close all running programs before you log out and then disconnect. I guess the big question is, do we have enough computers for 118 students in our class? And the answer is a big yes. Here is the plot I generated from last year's data. And you can see most of the time the computer usage is pretty low. And then it gradually picks up as we approach the due date, not surprisingly, around the due date, and we have this big spike. So as long as we do not wait to the last minute, and we use the simulator on our own machine most of the time, and only use the lab machine to test the code on board, then we have more than enough computers for user to remotely access. Now let's get started with HelloWorld. The lab manual is on GitHub. It is about 100 pages long. It is probably a little bit overwhelming to see such a long document, and then you may wonder where I'm going to start to read it and how I'm going to read it. So here's the guide for this week. Some sections I mark it as schemes, so that basically means you only quickly glance through them. We don't expect you to know the details about these sections. But for the sections that are marked as study, you really have to read these parts in details. especially how to connect to remote desktop. You have to follow the steps, and how to create your first HelloWorld application so that you get yourself familiarized with the Keil IDE functionalities, the debugger, the editor, the compiler, all these things. And then finally, what exactly is the CMSIS and its file structure, because we use this software stack from Keil or from ARM as part of our lab project. So now I'm going to show you, demonstrate how to create a HelloWorld application by using the IDE and run it under the simulator, and then run it on the actual board remotely. The detailed description of the demo is documented in Chapter 8. I'm now on the ECE RTOS 20, the school machine. So first we need to start up the MicroVision IDE. So usually you can just type uVision. So you will see this in the startup menu. But if you don't see it, then what you can do is you can go to C drive, software, Keil_v5, and look for uv4.exe, this green icon, executable, then double click it. So this is the IDE. To create a new project, we have some existing code on the GitHub. So if you go to the GitHub, I have the manual uploaded here, and I also have the manual code. Under the manual code, there are 3 folders for now. The util folder contains the source code or some scripts that are commonly used. So these are the source code. This contains the script. But these 2 folders, they are existing projects. You can directly run them. So I'm going to show you how to use the source code here to create a simple HelloWorld application and run on the board. So I'm going to go to my N drive. I have created a working space called SE350. And then here I created 2 folders. One is called Starter. The other one is called My Code. My Code currently is empty, and Starter is also empty. So now I'm going to start up the Git bash. To start the Git bash, just type Git, you will see Git bash. So I already have it, and I navigated to the N drive SE350 starter folder. Nothing's here. So now I'm just going to clone the repository. And you can see this folder gets created, and I got the manual code here. All I want to do is basically, I'm going to go to the util directory, and I'm going to copy the entire source code, Control A, Control C. And then I'm going to go back to my own working directory, my code. I'm going to create a folder called HelloWorld. So this is my folder. I'm going to create a source code directory, src. And I'm going to put all the printf related source code right here. The only thing that is missing is a main file. So we're going to create that main file later. So now let me go back to my starter code. I need to copy one more file, which is the script. So I'm going to copy it. I'm going to go here and put it under the root directory. So these are the template files I have. So now I'm going to go back to my IDE. I'm going to do project, new MicroVision project. I'm going to name it HelloWorld. So navigate to the folder where you have the project. You have to create the folder yourself. The IDE doesn't create the folder for you, but the IDE will create the project profile for you. So I'm going to save it. So now it asks me to choose the device. Our device is the NXP LPC 7068 microcontroller. So this is the one that I'm going to use. Now I'm clicking OK. So now the important step is to choose the CMSIS core. And the other one is the device files. And we need the startup files. So now I'm clicking OK. If you expand it, you can see 3 device files got created, like copied over to your
project folder, somewhere under your project folder. And this is the default source group 1. I want to let you know this basically is a logic view of your organization, of your source code. So the default target name is target 1. Let me rename it. Let's say hello world SIM. SIM stands for simulator. So now let me just change this name to something, I will call it the system code. I can create another group. Let's say add a group. I can call it source code. This is just to show you how to create groups. So again, these are logic views. So if you go to your project directory, okay, my code, you don't see this folder anywhere, like under source, you don't see it. You don't see it under the root directory either. So these are logic views. So now I'm going to add some code to this project. So first, let's just add the printf, the UART polling code. So double click, we'll add them, and I add close. I click close and I see these two files. Now I need a main file. So if you want to create a new source code file and add it to your project, first you need to create the file. So let me name it save as. I'm going to save it in the source, like main.c. So here's my main.c. It's very important. You have to add this main.c into your project. Otherwise, the project doesn't know the main.c exists. So before I type any real source code into it, let me just add it to my source code folder. Of course, I can add it to this group if I wish. Yeah, but just to show you, you can add files into different groups. So now here's the empty main.c. So instead of typing it, I'm just going to go to the starter file, which we have it on the GitHub, and there's a hello world there, and there's the main file. So I'm going to open it. Okay. I'm going to copy the contents of this file. So now I'm going just to paste it over. So this is my main file. Now what we need to do is to configure the target option. It's very important. We need to choose the version 5. The default is version 6. We unclick this iRAM tool, which is the piece of RAM we don't use, and then we go to output. Here, I usually want to select the folder for my target. So each target, I'm going to create a different folder for its object files. For example, the same target, I'm going to put it here. So I click OK. Similarly, for the output of listing files, I'm going to click here. This is my same target, and I'm clicking here. I'm OK. You can leave this as default. For C and C++, you can have C99 if you wish, and leave this one as empty for now. And for the linker, let's choose use memory layout from the target dialog. So we're using the memory layout in this target dialog. For the debugger, I'm going to use the simulator.
We also need to install the simulator initialization file.
And for the utilities, I do nothing. So now I'm going to click OK. So I'm going to build my project, and you can see no errors. That's good. So how I'm going to write? I'm going to first write under the simulator. To write under the simulator, I click the debug button, and then it stops at here. I'm going to go over the code. The code basically outputs strings to two UARTs. There are two UARTs on this board. The UART0 and the UART1. Under the simulator, the UART0 is UART number 1 because the simulator indexes things from 1. And UART1 is UART number 2. So I got like two UART window right here. So now I can basically reorganize my view so that I can see things more conveniently. So now I have two URs here. You can see these are the regular, like usual debug button. I can step over, system initialized, and initialize this first UR 00 and second UR 1. Now UR 0 will print howdy here. And then if I step over, UR1 will print hello world here. You can reset the target. Actually, you can reset everything inside the simulator. You won't be able to do it on the in-memory execution RAM target, which we're going to talk about later, but you can do it on the same target. So let's say if I do reset and then I run it again, then you can see it shows up here again. So this concludes our demonstration of how to run the program on the simulator. Now we're going to show you how to run it on the actual board. But instead of clicking this download button to flash the board, which is going to wear out the hardware, we're going to create a RAM target. To create a RAM target, you click the project, manage project items, and then you click new. So let me name my target RAM, and then I'm OK. So just ignore this error. So this target for now is exactly the same as the RAM, the same target we just created. We need to configure it for in-memory execution. To configure the in-memory execution, we click the target option. Here, we need to specify where we want the code and the RO data to be. So we want it to be in the first piece of RAM, which starts from hex code 1000, followed by another 4 zeros, 1, 2, 3, 4. So this is the starting address. So we split the RAM into half. So the hex code 4000, the first half, I'm going to use it for the code and RO data. And the second half, I'm going to use it for RW data and ZI data. So this basically is my new memory layout. So I'm going to do the output again. So now I have a RAM target. So I'm going to create a folder called RAM. And I'm going to save all the RAM target code under the RAM folder. Now I'm going to go to listing, and then I'm going to go to, I think I did it run, so I have to delete this folder. Yes, I have to go up and then create this RAM folder. And then I can put my listing here. User, leave it as default. Here, C and C++, no need to change. The important thing is I have to put this no CRP here, no code read protection. And for the linker, again, make sure this is clicked. For the debug, now I'm going to use the hardware debugger. I uncheck this one so that the program can stop when it enters debugger. An important thing is I need to execute this RAM ini script before I enter the debugger. So this script will load the code into the RAM. So very important, you have to have this file. And then I'm going to go to utility and then switch to this option, use external tool for flash programming. So that's all the settings, and then I'm clicking OK. So let me just build it. It builds. Now I'm going to minimize this window. So now we need to open up the real serial port. We use PuTTY to open the serial ports, but how do we find out where are the serial ports? You go to Device Manager, and then you open it. And then you go to Ports. You will see 2 ports here. Very important. Each machine has different port numbers. So you have to find out which port numbers through this way every time you log on to a new machine. So it is 7 and 8. So I remember this. And then I already opened 7 and 8 here. I'm just going to show you an important thing. So I usually save all these configurations as a profile. So I'm going to load it. An important thing first is the baud rate. So setting up here, and you need to make sure this is a serial. And then you go to serial. the baud rate is here. Leave the data bits 8, stop bit 1, no parity as default values. And this one, you have to change it to none. So this is the correct setting. I believe by default, it is X on and X off. Don't use this one, use none. Very important. Otherwise, it doesn't work. So to click OK. Yeah, when you try to open it, if it is already open, you will get an error. So anyway, so now let's enter. Let's basically run the code on the board. So when we say run the code on the board, basically we run the RAM target, and then we click this debug. Let me close this one. So these are from the previous simulator output. I don't need them. So now it stopped here. So now let me just step through system initialize. So initialize UART. So now let me just click. You can see UART0, hence this howdy. And then if I just click again, you can see UART1, hence this hello world. To finish, I can exit from the debugger. So this concludes our demonstration of how to run the code on the board by using in-memory execution. This is usually what you do when you debug your code on the actual board. Finally, I'm going to show you how to flash the board. So if I'm going to go back to my simulator target, and I go to target option, and I go to debug and settings, flash download, and I click reset and run. So this is the setting I just changed, and then click OK. I can rebuild my my target if I wish. And now if I just click this button, it will download the code to the flash memory. So basically, usually you do this once you have finished debugging and you're ready to ship the product, then you'll download this thing to the ROM, to the flash memory. So you don't do this very often. So but I want to show you how to do it, but don't do it very often because it's very bad for the hardware. So I'm going to just click load, and you can see the code executed, and you will see it is running on the real board. Another thing I want to, a little tip for everyone is here. If you run into some weird hardware problem and just can't explain, one thing we could do, or we usually don't do it very often, is basically come here and do a full erase of the chip. So erase full chip, and then you basically load the code to the chip. It will erase the full chip. It will do a full erase of the chip, and then sometimes it fixes the problem. But we normally don't do this very often. By default, it's erased by sectors.
We've just seen how to use the Keil ARM toolchain to create the HelloWorld and to run it. Now let's talk more about this toolchain. The Keil MDK5 is the main toolchain we're using. On the school computer, the software is on C drive, software, Keil _v5 uv4 folder. There is a uv4.exe executable that will launch the IDE. Please install this IDE on your own computer. This installation is pretty straightforward. I have two packages, like two links posted on Learn. The first one is the MDK core, so this is the main IDE. After the installation of the main IDE, it will automatically lead you to what we call the pack installer. The pack installer installs the device family pack, and what we need is the NXP LPC 7068. Then finally, we need the MDK v4 legacy support. So what about Mac and Linux users? Well, the recommended way is to install the Windows virtual machine on your Mac or Linux, and then inside that Windows machine, then you can install your Keil IDE. I have posted the VirtualBox installation guide and how to install like Windows on a VirtualBox on Learn. You may want to take a look at that. But what about those users who doesn't want to use virtual machine? For example, your processor may not be powerful enough to run virtual machine, or you just don't like it. Well, for Mac users, there are two options. You can use Parallels or Crossover. but they are all paid version software. These software will allow you to run Windows application on Mac. And for Linux, there's one, it's free, which does similar thing, allows you to run Windows application on Linux. I used one myself a couple of years ago, run the MicroVision IDE version 4 and worked pretty well. So now let me share with you some pitfalls. First of all, do not leave spaces in your directory name. This is a Nexus machine limitation, not the Keil IDE limitation. Second of all, the simulator is only good about 85% of the time. You should always test your code on the board. For example, simulator initializes certain memory regions, but the hardware does not initialize those memory regions. Certain bugs will only show up if certain memory regions are not initialized. So those bugs won't be reviewed by the simulator. And the simulator usually does not require certain hardware initialization. For example, the serial port. If you don't initialize it with proper baud rate or stuff like that, the simulator will still let you output stuff through the simulator, like simulated UARTs, but the actual hardware basically will not allow you to do that. And finally, simulator runs 1 or 2 orders of magnitude slower than the real time. It doesn't really matter to us that much most of the time, but once we start to do timing related things, you will start to appreciate the speed of the actual hardware. But does this mean you should avoid simulator? And the answer is a big no. Simulator is developer's friend. So how are we going to make good use of our tool? We will do small pieces. So let's do divide and conquer. Let's say I do a test and I test it on the simulator, it works, and then I further test it on board, it works, good, that passed, and then I move on to the next step. And using simulator is a common practice in real world. Now let's discuss some more about what is happening under the hood of the IDE. So the IDE comes with the ARM CC compiler and ARM ACM compiler. What happens is it's going to compile the C code into object code and the assembly code, which you didn't write, but the IDE automatically copied some startup assembly code to your project, and I'm going to show you later. And this assembly code also gets compiled into object code. Now all these object codes are linked together by the ARM linker according to certain memory layout. And then finally generate the executable. And for our case, it is the .axf file where we can load it to the board. So the HelloWorld application, we only create the HelloWorld main file. The rest of the files actually comes from the software stack called Cortex Microcontroller Software Interface Standard. So here's the microcontroller device, and then this particular one, the CMSIS core, that layer of software provides us lots of functions that we don't need to write, and that make our life to write the microcontroller application a lot easier. Recall when we were creating our very first application, we checked the CMSIS core, and we also checked the startup. So what happens is this CMSIS core, that's the software layer that supports our application. And then for our particular device, some startup files, for example, this assembly code, which we just talked about, and some system level C file and device header file got automatically copied into our project. So all these things, they are part of the CMSIS software stack. So let's take a look at the core file structure. So we only write this main file, and the CMSIS provides us the core, which is in purple color, and then the device specific file, which is in blue color. Recalling the HelloWorld main file, we make a function call of system init. This function is part of the CMSIS system initialization. This allows us to initialize the system in its default status with just one function call. And all these tools are device specific, and we wrote them, like I wrote them. To summarize, This week, you're going to install Keil IDE on your own computer, create your first HelloWorld application, run it on the simulator, and run it on the board by remote desktop. This brings us to the end of Lab 0 tutorial. Thank you for watching.